I'm Justin Braaten. I'm a developer relations engineer with the Google Earth Engine team. And today I'd like to do a data analysis session with you. And you can kind of think of it maybe as GIS 101. So kind of the simple things that you would do with raster and vector data, and also just kind of walk through how Earth Engine works. So just show of hands, who uses Earth Engine currently? And if you're an Earth Engine user, are you using the code editor? Raise a hand. How about Python API in some way? All right. Today, at the end, I'll do a demo, and I'll be doing it using the Python API in a Colab notebook, using GEE map for the interactivity and the map display viewing. So I'm glad to see that it might be new to some of you. Doing these kind of 101 courses, I always feel a little bit like, people aren't going to get enough out of this. And so I hope that at least if you have some background already in the basics of Earth Engine, that maybe I can provide just a little bit of a different lens. I always think it's helpful to hear somebody else talk about a technology or something, and I often learn something even if I am familiar with it. It's fun and nice to hear it from a different perspective, so hopefully everybody will get something out of this. So what is Earth Engine? And it's Google's cloud-based platform for geospatial analysis and data visualization. And it has three main components. We have a data catalog that's co-located with Google Compute. Sorry, I'm going to make it hard for the text here. I'll settle in here now. Okay. Yeah, so this big data catalog that is co-located with Google's servers. So when you make a request for some kind of computation, the data is right there. There's not a lot of transfer that happens, so it's very quick, and it's sort of like Google-sized compute at your fingertips. And the way that you access these resources and compute power is through the API, sort of the Earth Engine language. And so you use this language to write instructions. So on the left, I have this little block of code, and it's a function in Python, and it's called Earth Engine do a thing. And so I write code that I want Earth Engine to do these things to imagery, and this code I'm writing is in a client library. I write this code, I hit the run button maybe in the code editor, and then in the background, it takes the expression that I've just written and it converts it into this expression graph, which Earth Engine servers can understand. And that expression graph gets sent across the internet to Google's servers, and they get to work on your request, often breaking it up into many small pieces for multiple machines to work on in parallel. And then they put it back together in some, usually a reduced fashion, some statistical result, maybe map tiles that you want to view. And they send that back across the internet to your client where you can view it, interact with it, and maybe reuse it in some other bit of code. And so we can do this with two languages, JavaScript, which is primarily you would interface with it using the code editor. We also have a Python API. And these two APIs share a similar, almost identical syntax. Earth Engine's an object-oriented language, and so these objects are data classes, things like an image or an image collection, a feature. And each of these types of data have certain things that you can do with them exclusively. And so if you have an image, for instance, you could clip it to some region, you could sample a bunch of pixels, you could reduce a region of pixels into a statistic. And so whether you're working the Python API or the JavaScript API, it's with this Earth Engine language. And really the differences between Python and JavaScript are in how you declare the variables or a function or do a client-side for loop. And when I'm working with Earth Engine, I often think about sort of building things. I like to do a little bit of woodworking and kind of being handy around the house. And so in some ways, doing an analysis in Earth Engine feels like building a house or building a thing. And sort of what I mean by that is that you have these materials and you have these tools. The materials might be the data objects. The tools might be the methods, the things that you can do with these data objects. And then there's some process that you use these tools with these objects and manipulate them. And in the end, you get, in this case, a house. And it requires a lot of planning along the way, and often starts and stops and restarts. And I think that a lot of times people jump right into wanting to start manipulating. And I think that it's really important to understand Earth Engine's objects and their methods and understand what you want in an analysis sort of before you get to this part of actually the doing. Spend more time up front on understanding your materials, your tools, and what you want in the end. And to understand the constraints. So what you want maybe just isn't possible, and you have to kind of meet in the middle. And to get to understanding these constraints and having an idea for what you want, often there's quite a lot of experimenting, maybe coming from one side or the other, compromising and learning. And so let's learn about the materials and the tools of the Earth Engine trade. So we've got these two really ubiquitous geospatial data formats, raster data and vector data. And within Earth Engine, raster data are represented by the image class. And an image has pixels, it has bands, it has properties. And then an image collection is a series of images that share properties. Generally, they would have the same bands, and typically they are either in a time series. It's the same kind of data. Let's think about like Landsat, where you might have a time series, and you might have also images that span a large region. And so we call this an image collection. Similar data that exists kind of in this group, this set. And then we have vector data, and the most base level is just the geometry, the vertices that make up lines and polygons, and then there are point geometry as well. So that's just geospatial information. But then we can take that geospatial information and attach properties to it, and then we have a feature. So then you have an attribute table. Maybe this represents a protected area, and there's attributes that describe the agency that manages it, maybe the year that it became a protected designation. Anyway, so a feature is a geometry with attributes, and then a feature collection is just a set of similar features. So if we're talking about protected areas, there's a bunch of protected areas in California and Washington and around the whole world. We could put all of these, since they're similar, into a set. And there's so many other data types in Earth Engine. So those are the really common geospatial data sets, but then we also support the common data classes that you would find in other programming languages, like arrays, lists, dictionaries, numbers, string, date. And then also a set of more specialized data classes specifically for Earth Engine that deal with filtering collections, handling date ranges, classifiers, and joins. And so, we're learning about our materials, like what is available for us to work and build with. And there's a lot to kind of take in. And I think the best resource for sort of understanding what's available to you in Earth Engine is to go to the reference guide. So if you go to the Earth Engine docs pages, you'll find this reference tab. And then if you click on client libraries, you'll see this whole list in the table of contents. And these top level entries are the Earth Engine data classes. So this provides you the whole list of things that you can work with in Earth Engine. And so here's an example of an image. I believe this is Sentinel-2 image over the Tri-Cities in Washington, the intersection of the Columbia and the Snake River. And so our image has pixels and it has bands, but it also has a table of properties associated with it. So we know when this image was collected, the cloud cover, and a quality score, for instance. So this is our image type. And then an image collection, you could think of it just as a table of images. And so now our table, back here, it just included properties as an image. But when we talk about an image collection, the images sort of become a property within this table. So now we have two images. They share the same properties. They're an image collection together. And we could talk about a geometry object. And we have all of these options for what a geometry could be: line strings, points, polygons, multi-polygons. And when we make it into a feature, we still have this geometry with vertices, but now we also have an attribute table attached to it. So we know that this geometry has this ID. It's in zone 66, or it defines zone 66, and it's called rectangle 10. And there's any number of things that you could add to this attribute table. And then similar to image collections, a feature collection is just this set now. It's like think of it as a table of features that have geometries and then their properties. So we've been talking about the materials of Earth Engine, the things, the nouns, and now we can talk about the methods, the things that you can do with these materials, the tools that you have to manipulate them. And so, for instance, we've got our image, and some of the methods, the things that we can do with it are clipping it, sampling it, reducing it by a region. And there's a limited set of things that you can do with Earth Engine objects. This is one of the constraints. And so it's important to, when you know what data set, or excuse me, what data type you're working with, take a look at what you can do with it, what tools are available to be used with that data type. And so again, we're in the Earth Engine docs here under the reference tab, and I'm on the feature data set, and I can get a list of all of the things that I can do with a feature object. So just to wrap up, that it's really important to sort of understand the materials and the tools maybe before you get really started into an analysis. And also think about the endpoint, what your analysis, what you want out of it. Is it a vector? Is it a raster? What data type is that? And how do I get from the beginning sort of to this end? And then now I want to go to some considerations when working with Earth Engine that might be different than other geospatial analysis platforms. And one of the big ones is scale. So in image data, if we talk about Landsat, they have 30 by 30 meter pixels. We call it a 30-meter scale. And when you're working in Earth Engine and you do an analysis, well, maybe we should step back and we could talk about doing an analysis maybe in ArcGIS. And I've not used it in a long time, but back in like 2005, you would when you would run an analysis on the image, it's doing the computation in whatever projection that image is in. So the data source controls the scale. But in Earth Engine, the output determines the scale. So at some point in your analysis, you have to specify what you want this scale to be done at, what the processing scale should be done at. And we do this because Earth Engine, when we ingest the data, it has a native resolution. For instance, Landsat has 30 by 30 meter. But when you're scrolling in and out and visualizing your data, you want it to load very quickly. So if you're zooming out to a global mosaic, it's going to be impossible to load the zillions of 30 by 30 pixels. And so you need to have this tiled aggregation, these layers of imagery at different scales. And so when we ingest the data, we create the imagery at all of these different scales, and it's then available for you to compute sort of at whatever scale you'd like it to be done at. And a good example of this is in the code editor. When you are visualizing a map, you're not looking at 30 meter pixels when you're zoomed out quite far to a Landsat image. It is sort of grabbing whatever image tiles most closely match the zoom level. And you can also set the scale by the scale parameter. So if you're doing a reduce region option, you want to get the zonal statistics for some area, you have the option to set the scale. So at that point, you would say it's Landsat, it's 30 meters. I want this analysis to happen at 30 meters. I set it to 30 meters. You could also set it to 1,000 meters if you're just trying to get a real quick, look, is this analysis, going to work at all? And you don't want to wait for, to be processed at 30 meters. You could set it to 1,000 meters or 100 meters. The other thing that's a little bit different is the projection. Similarly, in other platforms, the input data determines the projection of the output, or of this analysis. But in Earth Engine, the result, what you want at the end, determines the projection. And so one example here is when you're visualizing something in the code editor map, let's say it's a MODIS image, which has sort of a funny sinusoidal projection. When you visualize it in the code editor, the map display is in Web Mercator. And so there's always a reprojection that happens. The last thing that we want in this case is the map display. That's sort of the output, and it is determining what the projection is. And since the map needs to be in Web Mercator, it does a reprojection to your image before it does anything else. So in this case, we're calling unit scale, which would take our MODIS image and scale values between 0 and 1. That's not important, but we're just we're applying some function to our image. But behind the scenes, because we've asked for it to show up in the Earth Engine map, it does a reprojection sort of behind the scenes. It didn't matter that the input data is sinusoidal. Because we're showing it in a map, it's going to reproject. We do have the option to specify reprojections throughout the process. There's a function called reproject, so we could reproject an image into whatever we like, and it will do that. But again, if we reprojected it and then we showed it in the map, it's going to do another reprojection because the last thing, the thing we want at the end, needs to be Web Mercator. So it's going to request it in that. This is like a sticky subject. And I guess maybe the point is that be really considerate and think about setting parameters all the time. If you're given the option to set a scale and a projection in a function, do it and know what you want, because that's what you're going to get. And yeah, so this is about the places that that determine the map or the projection. And if you don't specify it, you can get strange results. So there's a default projection. that comes up and catches people sometimes. So consider the case where you make a composite of Landsat images over a large region that includes multiple UTM zones. What UTM zone is it supposed to give you in the end? It doesn't know unless you specify it, but it has to do something, it has to show you something, and so it picks a default projection, and that happens to be WGS84, and the pixel size is 1 degree. And a funny thing that happens sometimes, people will do they'll do a composite, and then they'll do a reduced region on a really small area, something less than 1 degree, and they'll get back a single value, and they'll be well, that wouldn't happen in that case. There are cases where you get back what you're expecting to have like many values, and you get back a single value. This is what's happening. It's this default projection, which makes these huge pixels. So if you don't specify, sometimes this is what you get, is this weird default projection. And so what you want to do is be specific about, what this projection should be. So after you do a mosaic in an image collection, again, this is like multiple UTM zones. We make a mosaic out of it. Whoops. And then what we do to avoid this default, WGS84 1 degree cells, is that we can set the default projection. And in this case, I've set it to North American Albers. So yeah, be really cognizant about scale and projection, and set it whenever you get the option to do it. Oh, can we get you on the mic?
Use the microphone for the recording.
And so when you do that, you also take care of the scale? When you do the control the projections, what does it do with the scale? Does it do anything? Like, does it rescale to 1 degree?
Not at that point.
Okay, so when you do set default projections, it not only set the projections, but also the resolution.
It doesn't.
Okay. Okay.
That's a good question. I don't believe there is a parameter for setting the scale in. I could be wrong here. Let's just look. Well, no, I'm curious now. This is a good question. These are like the things that we're like wanted to get straight here. We do. Okay. And okay. Yes, so you have to set at least the CRS, the projection, and I believe the other two are optional.
The scale is not specified in the scale of the given projection.
Yeah. So these show up quite often in functions, and so whenever you see them, you should be setting them, and then it'll be really clear what is actually happening.
Is there an option to globally set these options? Is there a way to globally set these options so that across the program you have the same thing and you don't have to specify the parameter over and over again? We have a way in R. I was just wondering if we can do it.
No. The best you could do is, at the top of your script, for instance, set some constants, CRS transform and scale, and then keep calling them in. But typically you wouldn't have to you'd maybe only set these once at the end, like whatever thing you want at the end, set these on. Good questions. Thank you. And then the processing environments. Earth Engine has 2 processing environments. The interactive environment, and that's what you are getting when you're in the code editor and you're looking at a map or you are printing things to the council. It's interactive. You've made a request and you want an answer right now, or at least within 5 minutes. And so these it's a processing channel that is expecting things to finish quickly and they get it back to you quickly. So they have to be kind of small because it has to happen within 5 minutes, otherwise you get a timeout. But it is handy for quick prototyping. So it's things like, like printing to the console, getting map tiles that you're going to view. If you ever call get info to get a value, client side, or things like EE data compute pixels. Anything that's going to transfer data client side is in this interactive stack. And the limitations are 5 minutes. And often if you're trying to get a lot of data over, like a big feature collection, you only get 5,000 elements. Otherwise it'll say, no more, I can't handle that in this environment. And so if you do have bigger, processing tasks, you need to move over to this batch environment, which is simply EE export. So you are exporting your imagery or your feature collection to an asset, to cloud storage, to Google Drive. And this is a separate thing. It could take hours or days, depending on what your request is. And these both have different capabilities. The batch environment generally is able to handle tasks with a little bit that might require more memory, but they might take a little bit longer. So just something to be aware of, the limitations of these two environments, particularly the interactive environment. You can't expect the world, but you do get the benefit of quick interactivity for kind of small things.
Well, I see we're about to go to Colab anyway, but I was just wondering, is this the interactive environment, is that also within the Python API? Is that like the IPy leaflet widget?
Totally.
Okay.
Yeah. I'll mention that when we get into it. Yeah, so that was kind of what I wanted to talk about with Earth Engine. Get a good understanding of the objects, what their methods are, and how you can work within those confines to get what you want. And then the sort of considerations about working with Earth Engine with scale of projection and processing environment. And then I just wanted to go through a walkthrough of some analyses that you would do, maybe if you were in a GIS 101 course. And I'm going to do this in a Colab notebook. There's a little bit more setup involved with Colab and Earth Engine. So I'm going to be using the Earth Engine API. It's installed by default in Colab, but we've had changes this last week, and so I'm going to do an update to make sure we're on the most current version. It's typically updated every 2 weeks. So I've installing upgraded Earth Engine API, and then I'm going to also upgrade GEEmap. So GEEmap is what we use for interacting with the map and printing objects. And again, that is installed by default in Colab, but I want the most recent version. So I install the update there. I'm going to import these libraries. And then I'm going to authenticate and initialize. This is a step that you don't have to do. Oh, this is interesting. I don't get a box to import the token. Let me restart the kernel here. One more time here with that on.
Yeah, neither do we.
Go. You don't get it either? It should show up before.
You've got the two commands in the cell. If you separate them, the authenticate and initialize.
Let me try that. This has been weird this week, actually. It's inconsistent. I'll try to separate this time. You said separating works? Okay. Will you come up and do the demo? Yeah, it is working. I mean, this should work though. It's very strange. All right, let me. Sorry for the delay here. All right. I'm going to try not installing the updates to... Come on. All right. I don't know what happened there. That's really strange. Luckily, we know some people on the Colab team. If we can figure this out. So I'm authenticating right now. We're just making sure that I have an account with Earth Engine. I say that it checks out. I do. And I'm all set. I have this authentication token. And now I need a map and a console. And in Colab, you can add a scratch cell. So I want to have a cell on the side of the notebook that doesn't, that's always there. I'm going to call it a pinned cell. And so now you can see these two code blocks have been added. And I'm going to run this map one to get an IPy leaflet map. And that's where we'll be putting our map tiles that we're viewing. All right, so let's do a vector analysis. Start out with rivers in the Walla Walla Basin. I live in Walla Walla, Washington. I'm just kind of curious about this area. And so there's two data sets that we have that can help us look at water things. And so we've got free-flowing rivers and basins from World Wildlife Foundation. And then I have the rivers are lines and the basin's a polygon. And then I'm going to do central Walla Walla as a point. I'm just going to zoom in here a bit so we don't have to load so many map tiles over regions we're not interested in. So there's Walla Walla. I run this. And the syntax is really similar to the code editor. I have this map object. It's called M instead of uppercase map. And then I add the layer. And the inputs are exactly the same. And then we can see that we've got rivers now added. And if I zoom out a bit, we should be able to see the basins underneath in gray. And I've also displayed a few of these objects. So I've got my basins, which is a feature collection. And it's got properties. I can open it up. I can see that the type, I know it's a feature collection. So now I can look up and see what I can do with the feature collection in the docs. The version is for the date that this was imported into Earth Engine. I can see what properties are available. This is like the attribute table. This is the header telling me what properties are available and what data type they are. I can see all of the, well, in this case I've only shown you 10, but it will show you the list of the features in the feature collection. So each basin here is a polygon. And I can open it up and I can look at the properties for this particular basin. I was curious if they had a name in here. There's a lot of properties. Anyway, we can also have our point here. Open it up. We can see that it's a point. Now we know what we can do with it. If we look in the docs, we can see the coordinates. Yeah.
So what's the most recommended way to iterate through a feature collection or image collection?
What are you trying to do with it?
For example, apply a function to each of the elements or get some attributes out of the...
Yeah, a mapped function, and I'll go into that.
So you use like a map, and you say there's apply a function to the whole. So
yes, so it's like feature collection dot map, and then as the input you put the function that you want to run over every element.
Okay, got it. Thanks.
Yeah. All right, so we have these materials that we want to work with, and now let's do some things with them. Like filtering is a common thing to do. We can filter by attribute. We can filter by location, intersection, proximity, contained by, contained in, these types of things. So let's first do by an attribute. We want to get just the Walla Walla basin. And so if I run this piece of code, I'm calling a filter, and I'm saying I want the water basin ID to equal whatever Walla Walla's is. So I can do that with a string expression, or else I can use this ee.filter equal filter object, where I pass in the attribute field name and then whatever value I want filtered to. So if I run this, it finds the Walla Walla basin in the table, pulls it out, adds it to the map. So that was by filtering by attribute. Now we can do by intersection. So now I want just the river segments that are within the Walla Walla basin. So there's some geospatial intersection of these geometries. And so what I can do is I can again filter, and I can call the filter intersects function. Is that helpful or not to be bigger? I'm going to look at more code this way. Okay. And then we pass in the geometry. So we want the two geometries where they intersect. So our left field and our right value are the geometries. And then this is like the longhand. So in Earth Engine, there's multiple ways often to do things, particularly if you are filtering by date or region, there's a shorthand. So in this case, we're filtering by intersection, and it's kind of verbose, but there is this shortcut to just filter bounds, which does this exact same thing, just behind the scenes hidden. So if I run that, I get the intersection. I only want the rivers that are intersecting the basin. So there we go in blue. We can also filter by proximity. So now let's just get the river segments that are within 10 kilometers of central Walla Walla. So again, I'm doing a filter. This time the filter is a within distance filter. I tell it, how far to look out, and then I provide the geometry. So if I run that, you can see maybe in green there. Yep. That those are the river segments that are within 10 kilometers of Walla Walla. So now we've done some filtering, and then say we want to query some attributes. We're interested in river order. So each of these streams has a certain size and a volume that is draining out of it, and we're curious about that. So we want to make a visualization that shows river order as some color gradient. And in order to do that, we kind of have to know what the min and the max are, what the range of values are. And so let's query the attribute table and find out what, for this river order field, what's the min and max value in that table. So it goes through the table, and it gives us the max and the min. And we're doing that with the reduce columns method, and we're providing it this min-max reducer. So now that we know what the min and the max are, we can use that to style our visualization. So now I'm going to take this feature collection and paint it onto an image for visualization. And so I have this empty image. I make it into an 8-bit image for visualization. I paint on the Walla Walla rivers, and I want to assign the pixel value according to the river order. And I want the size to be 3. And then I visualize that image by specifying the min and the max and the colors. So now we can see river order by color. And so these white ones, there's not much coming out. There's not a lot of volume of water coming out. These are like sort of head of rivers. And then as we go downstream into the Columbia, we have a lower order, more volume. And then we could calculate the percentage of total Walla Walla Basin river length that is less than 7 river order. So again, we're just kind of filtering on attributes and querying attributes. So here I'm doing another filter. I want sort of rivers that have a lot of volume flowing out of them. And so now it has filtered down to these sort of main stem river sections in the orange. And then we could, these rivers are made up of a whole bunch of line segments, and each of them has a length attribute. So we could say, well, how long in total are these river segments of these main stems? And we could also ask it for all of the rivers and get a percentage of the main stem length to the total length of all rivers in the watershed. So I'm doing that again. This is reduced columns. If you think about feature collections as a table, I have a column and I want to get some statistic out of it. I want to reduce it. And so I'm going through the table. I'm looking at the length column and I want the sum of all the values in that length column. And I did that for all the rivers and just the main rivers. And then I divided these to get the percentage of main river in the basin, which is 21% is we could consider main river. So this is adding a little bit of math into the process. Another common thing to do is buffer. We could look at riparian zones versus upland. This would be really crude, but we could just buffer out from the rivers by, let's say, 100 meters. And so we've got our river feature collection. We're going to get only the geometry of it and then buffer the geometry 100 meters. And if I zoom in, you can see in orange we have the original line segment, and the black is the buffer around it. And then, so now we have our riparian zone, and then to get the upland, we could just clip our basin according to this buffered river riparian zone. And so I'm taking my basin, and I'm getting the geometry of it, and then I calculate the difference between the riparian and the full basin. And if I do that, you can see that's this orange outline here. We could hide other things so you can see it better. So it's been sort of cut out there.
I was going to ask, how do you get the list of the layers?
Oh, sure. Oh, right. I never showed this. Yeah, so some of the functionality of GEE map, right, there's a toolbar in the upper right corner. And if you click on this layers tab, then you have the option to turn layers on and off. You can set their transparency and all kinds of other style properties, similar to the code editor. All right, so now we have riparian and upland. And then we can also add attributes. A common thing you might want to do is add attributes to a table. So in this case, we'll do the distance to central Walla Walla. So for each river segment, how far is it from central Walla Walla? And this is the mapped function I was mentioning earlier. So we have this thing that we want to do. We want to calculate a distance. And we have to do this for every single river segment, so this is going to happen hundreds of times. So we write this function that we want applied, many, many times. And what I give it is the feature that we're working on, the river segment. And then I take that river segment and I ask, what's the distance to central Walla Walla? And I get back meters, and I want it in kilometers, so I divide by 1,000. And then to actually set this property, so now for this given river segment, I know the distance from it to Walla Walla, and I want to add that to this river segment's properties. I want to add a column called the distance kilometers, and the way that I do this is I take my feature, my river segment here, and I'm going to set a property, and I set this property name, distance kilometer, and then whatever was calculated, it's going to be set as the value for that property in that line segment. So now I have this function to do that, and I want to map it over all these segments. So I take my Walla Walla rivers and I call map on it, and then I map that function over all of the river segments. And what we get is the same feature collection, but now if we look at the properties of one of the features, we can see that there is this new distance kilometer that's been appended to the table. And then we could use that, again, we can reduce that column and get the mean distance from all river segments to Walla Walla. And I'm doing that with the reduced columns again, and this mean reducer. The answer is 23 kilometers is the mean from a river segment to Walla Walla. A join can be a common thing that you might want to do. One feature or one table to another table. In this case, I thought maybe we could take the properties of a census tract and add them to the river. And so what I'm going to do here is take in US Census Tract, add it to the map, zoom out so we can see a little bit better here. All right, so all of these purple lines are the census tracts, and what we can do is an intersection join, or join them by intersection. So whatever census tract a given river segment falls on, we're going to get those properties from the census tract and add them to the river segment. And so we do that through this intersection. So we were interested in the geometry intersection of these two things. And then it could be that there are multiple, a river section straddles two different census tracts. I'm only interested in whatever one is first. There's other ways you could do this. There's a save all, so you could retain all of the intersections. A few other joins that allow you to do different things, but just for this demo, I'll just keep it simple, and it'll just take the first one that it intersects. So I have to make this filter. I define what kind of join I want to do, and then I apply this join. I give it my primary collection, the thing that I want to add properties to, which is my rivers, and I give it the secondary table, the thing that I want to take properties from and add them to, which is my census tract, and then I tell it how to do this interaction, which is my intersection filter. And so if I do that, I end up with a feature collection and a new property that includes this tract, which is a feature. It's the whole feature attached to the table here. And so I can look into it. I can get the properties. Now I know what census tract intersected this line segment. This can be really useful, but also difficult to extract information out of because it's nested. And so what you could do is take the properties within this feature and copy them out. And so that's what I'm going to do here. I've got this function to copy these properties from the tract out of the feature. And again, I have to do this many times, so I'm creating a function and I map it over my rivers. And if I run this and I look at a feature, What did I pull out? All I wanted out of it was the tract ID and the name. So these should be in here now in the table. Right, so there is the name of the tract, and there's the ID, just directly within the river features properties.
Are these attributes stored in JSON files, or can they be exported as JSON files?
Yes, you could take this feature collection and export it as GeoJSON, or a shapefile, or CSV.
Okay. Okay.
Yeah, I don't know what happens actually with this feature. It might end up as a JSON structure, so you could have this kind of weird nested JSON. Yeah. Okay. All right, we're like close here, but yeah, go ahead.
Just super quickly, like I noticed that like when you're doing like basic math and things like that, you're not using like a Python operator or something. You're using a specific function from the GMap library. Is there a reason for that? Could you just do a divide, or do you need to do dot divide?
You need to do dot divide because those objects are only existing on the Earth Engine server. So this is, sort of having to understand about the data types. There's the Earth Engine objects that are server side, and then there are, your Python or JavaScript literal objects that are client side. It's confusing because you can use client side as parameters to Earth Engine objects, but not the other way around. Sort of comes back to like having to understand about all these different data types and when they are applicable. But you can write a string expression to do math. I'll cover that real quick here, which can make it a little bit easier, a little more shorthand. Okay, so I'll try to go through this raster analysis really quick. I've got Landsat imagery, top of atmosphere image collection, and I'm going to filter it really similarly. So I have this image collection. I define the path to it. I only want a certain range of dates. It's a few months in 2020. I only want the images that intersect the Walla Walla Basin, and the images have to be basically cloud-free. So I'm filtering by region, date, and an attribute. And I get an image collection object. I won't look at it too much here. You kind of get the idea about being able to look at properties. And then we can display this image. I just give it properties. I tell it what bands I want to visualize and the stretch. So now we have a nice false color. Here's the Walla Walla Basin. That's the city of Walla Walla right there. I can do image math to this. So let's say I want to include NDVI and NBR here. And there happens to be 8 images. So I need to repeat this process 8 times. So I'm going to write a function to do that. And in here, there's multiple ways you can do math. You can use these commands, as we were just talking about, these methods about math, about divide, add, subtract, etc. That's one way you can do it. Otherwise, you can use an expression, and you can write it out as a string. So here I'm saying NBR equals, sort of very common syntax in Python or R. The only catch here is that I have to tell it what these things mean in the expression. And so NIR, it doesn't know what that is. So I have to say that NIR is band 5, and I select it out of the image. And so if I run that, that's just defining the function. And now I map it over all of the collection, so I can add NBR and NDVI. And if I look at an example image, here are the original bands with the B, and I've added NDVI and NBR. This happens on all the images now. And I've got 8 images, and I want just one image, so I can composite them. I take my collection, and I reduce it in the kind of pixel dimension. And I want just the max value of NDVI. So whatever the NDVI observation that was the max, give me that and all of the corresponding bands from that observation. That's what I want. And so now I had 8 images. Now I have a single image we can see here with 13 bands. And it should have been displayed to the map. Let's see. Yeah, so these are all, that's the mosaic now. And then we could clip it. I'm clipping it to the Walla Walla Basin. NDVI. So now all we see is the Walla Walla Basin. We're showing NDVI. All the bands are still there, but I only want to show you NDVI. We could do zonal statistics. So we want to know what am I doing here? The median of the riparian zone and the median of the upland, so we can compare them. So remember, we have the buffer along the streams, which we're calling the riparian, and then we have the opposite of it that we're calling upland. And so the way we do that, zonal statistics, is with reduced region. We have this region of pixels. We want to reduce it to a statistic, and that statistic is the median. And so we say this is the area that we want to do it over. We want to do it at a 100-meter scale, just so this runs a little quicker, and only run the computation if it's less than this many pixels. And if we display that, so now we have values. So we've taken images and we've converted them into just floating point values here. So the median NDVI for the riparian area is 0.49. Upland's a little bit bigger. There's more pixels to deal with, so computation takes a little longer. So we can see that upland, it's drier. It probably doesn't have as robust vegetation growth and photosynthesis, so NDVI is a little bit lower. And then last here, let's just do a sampling real quick. 1,000 points. We have an image. We want to get some sense about a sample of the data in it for charting purposes. And so we have our composite of NDVI for the Walla Walla Basin. We call sample on it. We want to sample within the Walla Walla region. At 30-meter scale, we want 1,000 observations randomly from it. So if I do that, I get back a feature collection. And at the end here, I'll plot this data using pandas. So right now, what I'll get back when this prints is a representation of the Earth Engine object. It only exists on the server. What it's showing me is just some information about it. And so in order to plot it using pandas or some other kind of client-side library, I have to pull those data to the client, not just the metadata. I need the actual data. And so to do that, I can use EE-data, compute features, and the file format that I want to get back is a pandas data frame. So if I call that, you can now see this pandas data frame. So this is a table with, 180 rows, and it includes all of the band values. And I can plot it with Altair. So we can see a histogram, for instance, of NDVI. We can see it's bimodal. If we look, over at the map, we can see that there's these real, the vegetation is doing very well in some of these green regions, and it's quite dry and less robust in these other regions. And Altair is a really great package for visualization in Python. For instance, here we've got a scatter plot of 2 different bands, red and near infrared, I believe, and we can kind of see that there's 2 different clusters that correspond to these 2 different modes here. So that was a really quick kind of just overview of some simple things that you would do kind of GIS style, but with Earth Engine, and hoping to convey how to work with and understand Earth Engine objects and their methods. We are right on time, I think, so I could take questions if you want to stay a few minutes. I'm not sure what's up next.
Can you say a little bit more about how this division between client-side and server-side objects works? I guess I've seen something like that maybe with Spark data frames, you're kind of, is it in memory or is it, in a distributed object or something like that? But it's I don't know, it's not totally intuitive to me. So I'm wondering if you can maybe just say a little bit more about how that works.
Yeah. I mean, I think the Earth Engine, it can access terabytes and petabytes of data, which would be impossible to get to your computer locally. So there's just this sort of innate separation between all of this data that exists and Earth Engine's ability to compute on it and what is like physically capable of like getting to your computer. And so when you make a request, it's only sort of happening in theory until you say, I want something to come to me. It just sort of exists as a theory on the servers. Every time that I've printed these Earth Engine objects, it's done some computation and probably dumped it or cached some part of it. And all you're getting back is some metadata about it, this real small bit of JSON that can easily go across the web from Earth Engine server to your browser. This feature collection could represent a gazillion points and is 10 terabytes. We don't need to know that. We can just like look at the metadata. And similarly, when we're viewing images here, it did a whole bunch of computation, and all it's sending us back are tiny PNG images that are each, like 500 kilobytes or something. And so when you start wanting to request a lot of data client side, you're just really limited into what you could do. You could ask Earth Engine to calculate some composite over 100 years over the globe and ask for it client side using the high volume endpoint, and it would chug away at it sort of only as fast as it could give you the data over the internet. Does that help at all? There's just this huge bottleneck of having to send information to your computer, and so we try to send as little as we can to you. Yeah.
Following up on this, and I show my stupidity when it concerns to this. But so if it's too difficult to bring back data to your local machine, whatever, what people do, like if you want to save the product of an analysis, do you put it on a bucket, for instance? And it's too bad that your session was exactly at the same time as that session about import and export, because I think, yeah, so that's what you do.
That's what you do. So that was when I was describing the two processing environments. There's the batch environment.
Yeah. Yes. Okay.
And that's where you set up a task to run. I think it can run up to 10 days is the max. And what it's doing is it's computation, and then it's streaming files to some storage system, either Google Drive, Earth Engine Asset, or cloud storage. Okay. So that's how you get really large results, is to export them with the batch. So it's like EE.export image to one of these three options, and it just takes longer.
Is one of these three options more efficient than the others?
I don't really think so. I'm not sure how they have the Earth Engine servers live in the United States. I forget exactly what locations. But you could, if you had a cloud storage bucket, you could set it to be in the United States, and it might transfer faster. Yeah, otherwise Google Drive assets are maybe fastest, because that is Earth Engine infrastructure. Yeah. All right, well, thank you, everybody.